Hello everyone and welcome back. Today we're going to be continuing our exploration of single variable calculus and discuss a very important tool known as a Fourier series. So let's do a brief review of what a Taylor series and power series are so that we sort of know, what a Fourier series has and what it brings to the table. So let's assume that we have some function, for example, f of x is equal to sine of x, which we know to be a smooth function, i.e. it's infinitely differentiable. So if it's an infinitely differentiable function, i.e. a smooth enough function, then we can approximate it with a power series and moreover derive a Taylor series for it. And remember that the Taylor series for sine of x, centered around x is equal to 0, is given by x minus x cubed over 3 factorial plus x to the 5th over 5th factorial minus x to the 7th over 7 factorial plus or minus all of the odd powers of x divided by all the odd values of factorial, right? So we approximate a smooth function with a polynomial function, right? And in particular, I'm just using sine, which is a periodic function, but there are several other functions, for example, e to the x, that also has a nice representable Taylor series as well. So instead of approximating things with polynomial functions, Fourier series seeks to answer a different question. Can we approximate some function f with sines and cosines? Right, so instead of using polynomials, maybe we can approximate them with sines and cosines. So that's the obvious first question one may ask, but another natural question is, why would you want to? Because, polynomial functions work just fine, but maybe some functions aren't as smooth as possible. So, for example, smoothness might not exist for f. And another very important property is that polynomials are not bounded, right? Because if you have a bounded function and you approximate it with a Taylor series, then you're going to get a non-bounded approximation for that bounded function. But sine and cosine are bounded between -1 and 1, so maybe if you have a bounded function, a Fourier series might be a little bit more appropriate. Okay, so let's just go through a couple details. Let's just clean that word up a bit. It looks kind of crazy. Might not exist for some function f. Now let's get into a couple of the logistics of how to build a Taylor series. So let's just recall some Taylor series things. So recall that Taylor series are a special case of a power series. Some people get these two concepts slightly mixed up. So what is a Taylor's power series? So a power series, f of x, is an approximation in terms of powers. So in particular, one can represent a power series from the sum from 0 to infinity, some coefficients ak to be determined, times x minus c, sometimes known as the center of the power series, raised to the power k. So this is a power series representation for f, right? And if we take these coefficients ak to be equal to the kth derivative of f centered around c divided by k factorial, then this will turn this power series into what we would know as a Taylor series centered around c. And some people will say that if c is equal to 0, this is called the Maclaurin series of that function. So, to motivate the existence of Fourier series is actually a special case of what is known as a trigonometric series. Right? So we have power series and we have trigonometric series. So what is a trigonometric series for some function f? So a trigonometric series is one of the form f of x is equal to, again, a sum from 0 to infinity of ak times the cosine of kx plus bk times the sine of kx. Some people will change this slightly and make it k pi x or sine of k pi x, but we're going to keep it in this form, but you can always translate into those as well. So, some important things that come immediately from the properties of sine or cosine, in particular for k is equal to 0, we know that the sine of 0 times x is going to be equal to 0 for any x, and the cosine of 0 times x is going to be equal to 1 for any x as well. So therefore, we can represent f of x to be equal to a of 0, which is sometimes called the mean value of the trigonometric series, plus the sum from k is equal to 1 to infinity of your trigonometric series portion, cosine kx plus bk times the sine of kx. Right? So this is going to be the representation that we seek to build for functions. Right? So this is just a linear combination of sines and cosines. In particular, it's a linear combination of bounded periodic functions. All right. So one thing that needs to be chosen on our end, similar to how the center of the power series needs to be chosen for Taylor series, we need to choose. So we need to choose an interval, and this interval I, and I'm going to define it as from minus L to L to approximate f(om), right? Because keep in mind, cosine and sine are naturally built from, say, 0 to 2 pi or minus pi to pi or something along that line, because both of them have period 2 pi. So once you go out of that periodic phase of sine and cosine, it's just going to repeat itself. So if it happens to change for that function f, then this Fourier series is not going to necessarily pick up on that change outside of this interval, right? So generally speaking, you can turn this I into any interval a, b via transformations, but we're going to be assuming that the interval is symmetric about x is equal to 0. And more importantly, a common choice is minus pi to pi. In particular, because it has a length of 2 pi and it's centered around 0, which sine and cosine are typically going to be built upon. So this obviously has a period of 2 pi, which means it's nice for sine and cosine. But again, you can change this interval to pretty much anything you want. The math slightly changes and is a bit more complex or not as representable, I guess you could say, but it's definitely possible, but we'll get into those little things another day. Now, before I get into the building of a Fourier series, I just want to introduce a very basic function that you may have encountered in the past, and it's called the Kronecker delta function. And it's going to help us build a lot of nice identities for this minus pi to pi interval. And it's represented as delta jk is equal to 1 if j is equal to k and 0 if j is not equal to k. So as just a brief example, delta 5, 4 will be equal to 0 because 5 does not equal to 4, and delta 5, 5 will be equal to 1 because 5 is equal to 5. Now let's mention a couple trigonometric identities from basic integral calculus that you definitely should know. So again, let's suppose that our interval of interest is, and this is typically taken to be the open interval, minus pi to pi, meaning that L will be equal to pi. And you need to be able to prove the following identities on your own. I'm not going to prove them, but they are pretty easy to prove. The first exercise is the integral from minus pi to pi, so that's minus L to L, generally speaking, of sine of kx dx will be equal to 0. Another easy one is the integral from minus pi to pi of cosine of kx dx. This is also going to be equal to 0. And 3, the integral from minus pi to pi of sine of jx cosine of kx dx will be equal to 0 for any j and k. Now the more fun identities to prove are going to be the following, and these are actually going to be the more useful ones. So the fourth one that you should try to show is the integral from minus pi to pi of sine of jx times the sine of kx. So same function, different potential indices, is going to be equal to pi times Kronecker delta jk. So sometimes it's equal to pi, sometimes it's equal to 0, because delta is either 1 or 0. And then we're going to have the integral from minus pi to pi of cosine of jx, cosine of kx dx. This is also going to be equal to pi delta jk. So either this integral is going to be equal to pi or it's going to be equal to 0, right? And I highly recommend trying to prove all 5 of these identities on your own. So now that we have these basic trigonometric identities mentioned, now it's time to build our Fourier series. So keep in mind a trigonometric series is of the form, so the sum from k is equal to 0 to infinity of ak cosine kx plus bk times the sine of kx. And again, k ranges from 0 to infinity. And again, Fourier series is a special case of trigonometric series, just like Taylor series is a special case of Fourier series. So what I'm going to do is I'm going to consider the integral of this function f from minus pi to pi of f of x after I multiply it by the sine of jx dx. So I'm going to multiply both sides of this equation by the sine of jx, and then I'm going to integrate both sides of this equation from minus pi to pi. So it's important to notice that this function f must be Riemann integrable, else this expression doesn't make much sense, but I'm not going to get into the really small details of the theory. We'll get into that in another day, right? So in particular, in this statement, j only makes sense to be a non-negative integer, right? Because, k is ranging from 0 to infinity, so 0, 1, 2, 3, 4, and so on. Right? So what is this going to be? So if we write the right-hand side out, this is going to be equal to what? So it's going to be the sum from k is equal to 0 to infinity of, and let's go slow with this, so it's ak times the integral from minus pi to pi of the cosine of kx, since we're integrating with respect to x, everything that has x in it needs to stay inside of our integral. Here's our sine j term there. And then we have bk times the integral from minus pi to pi of sine of kx, sine of jx, dx. Right, so that's what we have. So what is this? So keep in mind, since we have opposite trigonometric functions multiplied, and k and j are any integers, because k ranges from 0 to infinity and j is an arbitrary integer as well, we know that this is going to be equal to 0, and that's obviously going to be true for all k ranging from 0 to infinity. And this particular expression here we know is going to be equal to pi times delta jk, because that's a sine times sine, and similar for our cosine times cosine. So once we simplify that, we're just going to be left with the sum from k is equal to 0 to infinity of just that bk term, so bk times the pi of delta jk. So what is this? So if we sort of expand this, if we're kind of new to the Kronecker delta function, this is going to be equal to pi times b0 times delta j0 plus b1 times delta j1 plus all the way down to bj delta jj plus all the way down to infinity. And keep in mind, that's going to be equal to 0, that's going to be equal to 0, all of those are going to be equal to 0, all of those are going to be equal to 0, and this is just going to be equal to bj. So we're actually just going to be left with that particular term there. So rearranging this, what are we going to have? So notice that we're going to have that pi, and then we're going to have that integral of f sine on the left-hand side. So solving this equation for bj, we're going to have that bj will be equal to 1 over pi times the integral from minus pi to pi of f of x times the sine of jx dx. And we get this wonderful, beautiful identity. And similar done for aj terms. Instead of multiplying both sides by sine, multiply both sides by cosine instead, and you can get the aj terms. So once we have that, then what are we going to have? So we have this trigonometric series that is given by f of x is equal to the sum from k is equal to 0 to infinity of ak cosine of kx plus bk times the sine of kx. And now we have the special terms for ak and bk. So this is what we refer to as a Fourier series. So Fourier series takes these coefficients ak, so bk we've already proven to be equal to 1 over pi times the integral from minus pi to pi of f of x times the sine of kx dx, and one should be able to see or prove on their own that ak will be equal to 1 over pi times the integral from minus pi to pi of f of x times the cosine of kx dx. Now, for a0, remember the mean value of the Fourier series is typically isolated on its own and typically for good reason. So let's figure out what that will be. So keep in mind, this is going to be equal to what? So this is going to be equal to f of x is equal to a0 plus the sum from k is equal to 0 to infinity of ak times the cosine of kx plus bk times the sine of kx. So we need to figure out what is a0. So if I integrate both sides of this equation from minus pi to pi, so integral from minus pi to pi of fx, and I'm not going to multiply by sine kx or cosine kx, I'm just going to integrate. So what we're going to have is, we're going to have the integral from minus pi to pi of a0 dx, and then we're going to have the integral from minus pi to pi of this series, ak cosine kx plus bk sine of kx, and that's going to range obviously from k is equal to 0 to infinity with respect to x, but keep in mind that those integrals are going to be equal to 0. Those integrals are going to be equal to 0 because we're going from minus pi to pi of just cosine and by itself and sine by itself. Those are those first two identities. So this entire integral is going to be equal to 0 as well, and then it's just going to vanish. So what we're just going to be left with is this term right here. So we're going to be left with the integral from minus pi to pi of f of x dx will just be equal to a of 0 times pi minus negative pi, which is just going to be equal to 2 pi. And then we can just solve this equation for a0. So a0 will be equal to 1 over 2 pi instead of 1 over pi like the other two, times the integral from minus pi to pi of f of x dx. So now we have that special representation for 0, for a at least. And keep in mind, b0 will be equal to 0 because of the point that I made earlier. So now we know how to build Fourier series, and we know how to build it from trigonometric series. Let's actually work through an algebraic example to sort of see how Fourier series can be built for a very commonly known function that's not necessarily periodic. So the function that I want to build a Fourier series for, in particular on minus pi to pi, is going to be the absolute value of x function. Now the reason I choose this particular function, even though it is a very nice v-looking graph, is because it doesn't have a Taylor series in the middle of the interval, in particular at 0, because the function isn't differentiable there. So you can't build a Taylor series for this function around x is equal to 0. So Fourier series might be able to fix the problems the Taylor series has for this particular very famous and elementary function. So let's go ahead and start to build these coefficients. Some people call them the Fourier coefficients. So let's start off with a0, the mean value of the Fourier series, and that's going to be equal to 1 over 2 pi times the integral from minus pi to pi of our function absolute value of x. So keep in mind this function is symmetric about x is equal to 0. It is an even function, so the area to the left will be equal to the area on the right of 0. Right? So what I'm going to do is I'm going to write this as 2 divided by 2 pi times the integral from 0 to pi, and then on the right hand side that's just going to be equal to y over y equals x. So I'm just going to write that as x dx. So these 2's cancel for our coefficient, and then we're just left with pi, and then what are we going to be left with? So we're going to have 1 over pi, and then the integral of x we know is 1/2 x squared, and then we need to integrate that from x is equal to pi, x equals to 0, and subtract. So that's just going to be equal to pi squared divided by 2. So that's going to be giving us, or pi squared divided by, oh, and let's not forget our 2 pi on the bottom. So that's actually going to be equal to pi over 2. So that's going to be equal to our a0. So let's box that off just in case we forget about it. Now we have a0. Now we can go for ak, for example. So what is ak? So the general form for ak for k bigger than or equal to 1 is going to be equal to, actually, let's do bk first. Let's do bk. So bk will be equal to 1 over pi times the integral from minus pi to pi of our function, absolute value of x, times the sine of kx. Remember, ak is for cosine, bk is for sine. Now you might be thinking, why would I want to find bk first? Well, keep in mind this is an even function, this is an odd function, and you should know from math fundamentals that even times odd will be an odd function. So we have an odd function on a symmetric interval about 0. So this is pretty much like the sine function from minus pi to pi. And we know that that integral would be equal to 0, right? You should be able to verify that on your own. So this is equal to 0. So we have 1 over pi times 0. And that's obviously going to be equal to 0. So all of our bk's will be equal to 0 regardless of the value of k. So now what I want to do is just focus on my ak terms. Now keep in mind, since bk is equal to 0, we immediately have that absolute value of k expressible as a Fourier series. It's just going to be equal to a0 plus the sum from k is equal to 1 to infinity of ak times the cosine of kx, because all of our bk values are equal to 0. So before we even find our ak terms, even though we've already found our a0 terms, this is a sum of even functions, right? And that shouldn't be surprising to you because the absolute value of x is an even function, so the even function should be expressible as the sum of even functions. And this is sort of reminiscent of Taylor's series where we have cosine, and that's expressible as an even degree polynomial. So let's go ahead and see if we can find a nice representation for these coefficients, ak. So what is ak going to be? And this is for k greater than or equal to 1. So that's going to be equal to 1 over pi times the integral from minus pi to pi, our function, the absolute value of x, times the cosine of kx dx. Keep in mind this is an even function, this is an even function too, therefore the product of two even functions is also even, meaning that it's symmetric about the y-axis, so I can rewrite this similar to before by factoring out a 2, so 2 divided by pi, and then integrating from 0 to pi instead, which means the absolute value of x is just going to be equal to x, and then we're going to have a cosine of kx dx term there. So this type of integral structure is very reminiscent of something that we can usually do integration by parts for, which keep in mind is just the integral of u dv or uv minus the integral of v du, where u is going to be taken to be x and dv will be equal to cosine of kx. I recommend you do this exercise on your own just to make sure you're familiar with integration by parts. It's a nice little practice problem. But once you do it and simplify everything, you're going to get the following. So 2 over pi, and then you're going to have x over k times the sine of kx plus 1 over k squared times the cosine of kx. And then this is going to be evaluated at x equals pi as x goes to 0 and then subtract. So let's take our time with this simplification. So we're going to have 2 over pi, and then we're going to have what? So x is going to go to pi, so we're going to have pi over k, and then the sine of k pi, plus 1 over k squared times the cosine of k pi. Now let's plug in 0, so it's going to be minus 0 over k times the sine of 0k minus 1 over k squared times the cosine of 0k. So what do we have here? What do we have here? So obviously 0 times anything, that's going to be equal to 0, so that's not going to be very exciting. And the sign of pi is going to be the sign of 0, so that's also going to be 0 as well, so that disappears. And then what are we going to have over here? Well, the cosine of 0k, that's just going to be equal to 1. So that's going to be equal to 1 over k squared with a negative sign in front. So let's actually just simplify this. So we have 2 over pi times, so we're left with 1 over k squared times the cosine of k pi minus 1 over k squared. So what can we do with this expression? Well, it's very obvious to see that 1 over k squared is a common term for both of these expressions. So we can write this as, let's say, 2 over pi times 1 over k squared. And then times, well, cosine of k pi, we know that's just going to be equal to minus 1 to the power of k. And then we're going to have that to be equal to minus 1. So this is an expression for ak, for k greater than or equal to 1. So what is this going to be? So when k is even, what is that going to be? So that's going to be equal to 2 over k squared pi. When k is even, that's going to be equal to 1. So it's going to have 1 minus 1, which is obviously equal to 0, and this is for k even. And then for odd, we're going to have 2 over k squared pi minus 1, which is going to be equal to minus 4 all over k squared pi, and that's for k odd. So the only thing that really contributes is the odd portions of k, right? So from here, now we can start to simplify everything. And keep in mind, our trigonometric series, or our Fourier series, is given to be as follows so far. So a0 came out to pi over 2. And we're going to be left with this minus 4 coefficient because, minus 4 times 0 is going to be 0. So we can technically factor minus 4 out of the 0 terms too. And then we're also going to be left with a pi coefficient on bottom. So we're going to be left with minus 4 over pi. And then we're going to only have the odd terms since all the even terms are gone. So it's going to be 1 over 1 squared times the cosine of 1x, and then plus 1 over 3 squared times the cosine of 3x, and so on. All odd integers up through infinity. So we can represent this as follows. So here's our final result. So the absolute value of x will be equal to pi over 2 minus 4 over pi, and we're going to express this as a nice little series. So the sum from k is equal to 0 to infinity of the cosine of 2k plus 1 x all over 2k plus 1, the quantity squared, right? And this is for x in minus pi to pi, and that is the Fourier series of this function on minus pi to pi. So if we want to approximate the absolute value of x on, because we typically can't go to infinity, we can say that this is approximately equal to pi over 2 minus 4 over pi times the sum from k is equal to 0 to capital N of cosine of 2k plus 1x all over 2k plus 1 squared, obviously for large M. So once you have that, then it can start to approximate. So what you're actually going to have for your final result is the following. So it's obviously as n goes to infinity, you're going to get the absolute value curve, and that's going to range from minus pi to pi. But keep in mind, outside of this region, Fourier series can't really capture that behavior. So what you're actually going to see is it's going to repeat there, and it's going to repeat there. So this value here, that's going to be 2 pi again, so that's going to be equal to minus 3 pi. And this value right here, that's going to be equal to 3 pi as well. And obviously outside of that interval, you're going to see it bounce up again, right? So it's almost like an absolute value version of the sine function. It's almost like the absolute value of sine, right? So that's obviously going to be equal to 5 pi. That's going to be equal to minus 5 pi, right? And that comes from the Fourier series of the absolute value on minus pi to pi, right? So this is just a basic example of Fourier series and also how to build them. Several things need to be mentioned about theory, but we'll get into that another time. But I just wanted to introduce Fourier series too, because this is a very powerful tool. So I hope you enjoyed this video, and I'll see you in our next exploratory adventure. Thank you, and see you then.